All right, welcome to the AUA video week 4. AUA stands for Ask Us Anything. Once again, we're taking questions specifically related to the content that we talked about in the video lectures this week. So let's dive right in. So the first question comes from Robert, and Robert asks lots of things, but I'm just going to pick out one particular one here. What do you consider your field's greatest success? So let's just open that. Okay. Start with David.
So I'm a behavioral ecologist, and I study non-human animal behavior, and I study it in the context of the environment, and one important part of that environment are parasites. So I'm interested in how parasites control the behavior of the hosts, moving them around to some location to die. And I think the greatest benefit in the last few years, or greatest advance, is that we've sort of rediscovered natural history. We've in some ways been able to go back into the field and do a lot of complicated studies with the advantage of cheap and affordable technologies, which allow us to see in great detail the interactions between parasites and hosts in ways we haven't done in the past. And this is really beneficial because it allows us to open up rather interesting avenues of research. For example, how parasites control the behavior of the host in very fine, detailed ways. So that would be, for me, the greatest advancement in the last 10 years.
So I guess my area is in quantitative epidemiology and tracking trends through time, fitting models to those things, and trying to do prediction. I think one of the biggest challenges to that is that the large volume of data that we have is partially observed or measured with error or underreported. And I think there's been a lot of recent advance in statistical methodology specifically for dealing with partially observed or underreported data. And without getting too deep into the technical side of this thing, there's a class of models that are referred to as state space models or hierarchical models that allow us to both fit processes through time or across space, but also to explicitly account for aspects of missing data and underreporting or partial reporting. And I think what that's allowed us to do is to make much better use of the observed trends that we see in public health surveillance to get directly at the mechanistic aspects of the underlying epidemiological processes.
So, like Matt, so I'm a computational biology, so a lot of my work is to do with trying to use mathematical or computational tools to try to control disease dynamics. And I think this is going a bit further back in time than Matt and David, but I think it's one of the really crucial insights in the field is the notion of herd immunity, and the notion that you do not need, in order to stop an epidemic, you do not need to deal with all individuals. You do not need to immunize all individuals. You just need to immunize a critical fraction. And we'd be talking about this a lot in the course, but that critical fraction is related to the basic reproductive ratio. So, for example, for smallpox, the critical key insight from the models was that we only need to vaccinate around 80% of our target population in order to stop the smallpox epidemics. And indeed, I think an enormous success that if we look at smallpox eradication, then broadly speaking, we did see that the chain of transmission was broken and the disease locally eliminated whenever vaccination cover exceeded that. And I think we've seen similar successes also with elimination for things like measles, where I think that I think that's very, very important because that's very simple results that directly guides all the recommendations of bodies like WHO in their daily attempts of reducing the burden of disease.
Yeah. Yeah, so I would say 3 things. I would say the whole sort of emerging field of complex systems or complex networks that really got started maybe 15 years ago, in all earnest at least. That's, in my view, brought a lot to the field of epidemiology. Just in conceptually understanding how populations are structured in social networks, or contact networks perhaps more appropriately, and along with that the development of tools, mathematical tools or computational tools to understand the processes on these networks, identify people who are perhaps at the largest risk based on their network position, and so on. I think the other thing is the internet, very broadly speaking. It's a bit broad, but it still has only been with us for 20 years. There's this really nice paper, I think by Chen et al., where they've shown the extent to which the time of disease or outbreak onset and reporting of that disease has gone down. So the internet has really helped to reduce that time span quite rapidly. And now in that same vein, we're now in this sort of social media age where everybody to some extent is a reporter. And how that's going to play out is actually something that remains to be seen, and we'll talk in another question a bit more about this. But that seems to be changing reporting and disease surveillance in general. It seems for the better.
So I would say, I'm going to move down to the molecular scale because I'm a molecular biologist, that the single most important discovery is that of an enzyme called reverse transcriptase. And it's the enzyme that comes from the virus family called retroviruses, and HIV is a retrovirus. And the viruses that David mentioned that make up about 8% of the human genome are also retrovirus etiologies. And so why is this important? It broke a paradigm, and things that break paradigms are often very interesting for us in the sciences. It allowed us to investigate this very important type of virus, but it also really led to the advent of the field of molecular biology, because it gave us the ability to take RNA, which is difficult to work with, and convert it into DNA. And that has repercussions across all fields of infectious disease, because many of our emergent viruses are RNA viruses, and now we have molecular tools in which we can actually begin to study these. And one, I think, very important outcome of that is that there's a lot of viruses out there that aren't causing disease. Okay, we have a lot of viruses in the population. We couldn't detect them, prior to having this technology, this molecular biology technology. If they didn't grow in culture, we didn't know they were there. So it really, that single discovery really opened up a whole field and really, I think, transformed how we can investigate infectious disease at population scales.
So I'm going to go back to the middle level. And I'm actually going to call back on the social sciences, on the system sciences integration. So for a long time, we've had a good sense of what social support and social capital and social networks may play. But we've had these models that have assumed either that everybody's connected in a regular format or at random. And we know that there are non-random patterns to interactions and non-random predictable patterns to how people will isolate themselves or do social distancing, and the time and dynamics of those have played really important roles in understanding, well, then how do we help people get what they need to get in order to have the right kind of social support? At first, we just did numbers of people, right? More as being better. And we've learned very well and very quickly that more is not always better. There's actually a structure in which people need to be embedded that facilitates the best kinds of access to new information, or the best kinds of regulation of positive kinds of behavior, being able to see those and place those within the patterns of communication that's going on and then behavior, and knowing that these are dynamic. As soon as I go to persuade you and it doesn't go well, you may not interact with me, and those patterns keep changing. As we can understand the dynamics of these networks, these non-random networks, and the role that the messages play within them, we've had this real nice, actually going back to old questions, like how do we develop rumors, and what's the role of rumors, and what does social capital look like? What is the structure for that? How do we facilitate the right kinds of distancing, or what does the herd need to look like that everybody could get immunized in the right way, and we can actually get the immunity instead of, well, everybody who didn't get vaccinated all ended up together. So it's been this nice play where we can actually go back to old questions, I would say.